We use numbers constantly, but analysis eventually asks what these objects are and which properties we are actually allowed to use. Today we begin with the Peano axioms and use recursion to define addition and multiplication. Then we will make 1 + 1 = 2 under adult supervision. Number systems are enlarged when familiar operations stop producing answers inside the system we already have. Natural numbers support counting, integers repair subtraction, and rational numbers repair division. Real numbers repair missing limits, while complex numbers repair missing polynomial roots. The inclusions show how the systems fit together. A construction must also define every new operation and prove it is consistent. The purpose is to separate assumptions from consequences. Mathematics dislikes undocumented dependencies almost as much as software does. A terminology check first. The Peano axioms describe the natural numbers, not the full system of integers. Negative integers require a later construction. Dragging them into a proof of 1 + 1 = 2 would be ambitious baggage handling. Axioms characterize the behavior of zero and successor, while set theory can provide a concrete model realizing that behavior. The Peano axioms are categorical. Any two systems satisfying them have the same structure up to a unique isomorphism. A Peano system has a set of natural numbers, a distinguished element 0, and a successor function on that set. 0 is not the successor of any natural number. The successor function is injective, so equal successors must come from equal inputs. Finally, if a subset contains 0 and contains the successor of each element it contains, then that subset is all of the natural numbers. 0 starts the chain, successor advances it, and induction says the system contains nothing outside that chain. Notice what is missing: addition and multiplication. We do not get to smuggle the desired operations into the axioms and later act surprised to find them. Let E contain 0 together with every successor. The set E contains 0. And whenever it contains n, it certainly contains the successor of n because every successor was placed in E. Induction therefore forces E to equal the entire set of natural numbers. Thus every non-zero natural number is a successor. Its predecessor is unique because successor is injective. This matters for recursion. Every input is either the base case or reaches us through exactly one predecessor. Ambiguity has nowhere to hide. The recursion theorem turns a starting value and a rule for taking one successor step into a function on all natural numbers. Given any set x, starting point x sub 0, and function g from x to itself, there exists a unique f satisfying these equations. Existence comes from building values along the successor chain. For uniqueness, two candidate functions agree at 0, and agreement at n forces agreement at its successor. Induction then makes the two functions equal everywhere. That unique function will make our recursive operations well defined, rather than hopeful patterns decorated with ellipses. To define addition, fix a natural number m and apply recursion inside the natural numbers, starting at m and repeatedly applying successor. The recursion theorem produces exactly one function f sub m with these base and successor rules. We define m plus n to be f sub m of n. Equivalently, m plus 0 is m. And adding a successor means taking the successor after adding the predecessor. Existence gives an output in the natural numbers, and uniqueness makes that output unambiguous. Addition is well defined. Multiplication is defined only after addition, because one recursive multiplication step adds another copy of m. For fixed m, Recursion gives a unique function h sub m that starts at 0 and adds m at every successor step. We define m times n to be h sub m of n. Thus m times 0 is 0, and m times the successor of n is m times n plus m. The same existence and uniqueness theorem makes multiplication well defined. The order matters, addition first, multiplication second, circularity never. Numerals are abbreviations built from successor. 1 follows 0, 2 follows 1, and 3 follows 2. In the von Neumann model, 0 is empty and the successor of n is n together with n itself. This is one concrete realization of the Peano structure, not a new arithmetic axiom. The axioms also ensure that 2 is not 1. Equality would let injectivity force 1 to equal 0. But 1 is a successor, while 0 is not a successor. Therefore 2 and 1 are different. So the symbols 1 and 2 name genuinely different natural numbers. Standards remain demanding even for extremely small integers. Now begin with 1 plus 1 and replace the second one by its definition, the successor of 0. The recursive clause for addition says that 1 plus the successor of 0 equals the successor of 1 plus 0. The base clause says 1 plus 0 equals 1, so the expression becomes the successor of 1. But the successor of 1 is exactly how we define 2. Therefore 1 plus 1 equals 2. Every step follows from a displayed definition. No appeal to fingers, apples, or institutional tradition was required. The Peano axioms characterize the natural number structure using 0, successor, injectivity, and induction. The recursion theorem converts step-by-step rules into unique functions on all natural numbers. That theorem defines addition first and multiplication second, proving both operations exist and are unambiguous. Their recursive equations are consequences of those definitions and determine every finite computation. With 1 and 2 defined as successive successors of 0, the equation 1 plus 1 equals 2 follows in 4 justified steps. Elementary arithmetic survived the audit. It was less effortless than childhood advertising suggested, but considerably more reliable.